this is matrices. Matrices, the determinant is like a property, and there are lots of great things that happen as long as the determinant is not zero for a matrix, and that it gets all of this stuff when you go a little deeper into linear algebra. Like some of you, if you're going to go into engineering, you'll spend a lot of time you'll take a whole course that's linear algebra. It may be called something else, but it's basically matrix operation stuff. And if the determinant is not zero, you get all of these things happening for you. If the determinant is zero, then none of that stuff happens, and that's kind of important out of that. But that determinant is a property of that. It's a number that tells us something about that matrix, but it's like a property, so it really doesn't serve a whole lot of purpose for us in general. As far as this class, just kind of intro to it, but it does. It's just like a property. It's like the wall is white or green or whatever. Yeah. So, all right. So let's look at a determinant of a 2 by 2, and the notation that they can use for that is they use DET. A, B, C, D. A, B, and C, and D are just numbers. So they might use that notation for that. Yes, sir. And determinant of a 2 by 2 can be done in the calculator, but I don't ever do it in the calculator because I'm faster to do it by hand. You will be too if you know your multiplication tables, because the way you find the determinant of a 2 by 2 is you cross multiply A times D minus B times C. Okay, that is how you find the determinant of a 2 by 2. It's not how you do any other size, but a 2 by 2, that's how you do that. I'll show you how to do it on the calculator as well. But the big idea here is it takes me longer to type it in than it would just do that multiplication and subtract, honestly. So that's why I don't do that in the calculator. The other notation that they could use would be this. Looks like absolute value bars. Instead of brackets around there, it's just straight up and down bars, like absolute value looking bars. That also means determinant. They kind of bounce back and forth which notation they use. It just know both of those are asking for a determinant. So if it's just straight up and down bars, that's determinant. Or if it says DET and then has a matrix there, that's determinant. Both of those mean determinant. AD minus BC. Still going to do that. So let's do a 2 by 2. 3, negative 2, 7, 5. Then the absolute value bar, so that tells us to do the determinant of that. So 3 times 5 minus 7 times negative 2. 15 plus 14 is 29. Straightforward. Very straightforward. Now, to do that with a calculator, I'm going to clear my screen there. I'm going to go to the matrix menu, and I would enter in a 2 by 2 matrix. And we're going to need to know how to do this with the calculator anyway, because when we get to larger ones, you definitely don't want to do those by hand. Not with a time crunch on us anyway. So I've entered in that matrix, and now I want to do the determinant of that. So I'm going to go to the same place that I went yesterday to do the RREF stuff. I'm going to go to the matrix menu, go over to math, but I don't have to scroll anywhere because the very first option is DET, it's a determinant. So I'm going to pick that one, and then I just need to tell it what to take the determinant of. So I pick my matrix that I put it in there with. And tell it to find that determinant, and it's 29. Wait. And all the time that it took me to type that in and go get that command and everything, on a 2 by 2, it's definitely quicker to just do the multiplication and subtract. So that's what I would suggest that you do. Now, on a larger matrix, say maybe they ask us to find the determinant of 2, negative 1, 3, negative 2, 5, positive 1. 0, 6, negative 9. That's what size is that? 3 by 3. It's an n by n matrix, square matrix, so you can find the determinant of that. Doing it by hand is not quite as easy. There are far more operations. For a 2 by 2, there were 3 operations. For a 3 by 3, you would end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 24 operations to do it on the 3 by 3. Imagine what a 4 by 4 has. It piles up very, very quickly. It's really an exponential growth in the number of operations that you have to do to find a determinant. So we don't want to do this by hand. There are multiple ways to do it by hand. When I was in college, I had to do them by hand. I liked it. It was enjoyable to me because it was neat to be able to do it different ways to get the same answer. Most people don't find enjoyment in that. So 3 by 3, anything bigger than a 2 by 2, I'm doing in the calculator. That's bottom line. So let's put that matrix in our calculator. Second matrix. Edit. I need a 3 by 3. I'll just put it in matrix A. 3 by 3. And then I'm putting in that matrix 2, negative 1, 3, negative 2, 5, positive 1, 0, 6, negative 9. And then you get negative 120. You typed in everything, that's what we should get. Negative 120. Amazing. Nothing really spectacular about determinants. They don't really, we're not using them to do a whole lot with here. It's a property of a matrix. That's what I want you to get out of that. Now, there is, by Coach Mack and I's standards, we try to cover certain things, and I am obligated to show you that Kramer's rule, what it is. Kramer it was a mathematician from many moons ago, and he worked with matrices a lot and systems of equations, and he came up with a way to use determinants to solve systems of equations. We already have the Gauss-Jordan method or RREF that we use already, and it works wonderfully, and it actually even helps us to get the solutions when it's infinitely many to be able to write those. Kramer's rule doesn't do that. It doesn't get us a nice equation to work with infinitely many solutions. It would tell us that exists, that the answer is infinitely many solutions, but it doesn't do that. But Kramer's rule is just a way, and this is just something you need to know, of solving systems using determinants. And you actually end up taking the determinant of, depending on how many variables you have. So if you have got 2 variables like x and y, you would end up taking 3 different determinants to find the answers to that system. If you had 3 variables, you'd take 4 different determinants to find that solution. We're not going to use Kramer's rule. I just want you to, if you ever encounter somebody saying, hey, use Kramer's rule to solve this system of equations, remember, it's solving a system of equations, so you can use RREF, and that's the same. It's going to use the same solutions that they would get with Kramer's rule. Okay? So I just want you to know that Kramer's rule is a way of solving systems using determinants. We're not going to do it that way. We've already got a good method. RREF works great. Gets us actually a little bit better things on infinitely many solutions than Kramer's rule does. Okay, so that's what you need to know about determinants. All right. Next thing, operations with matrices. Stuff you've seen before. The first thing we're going to talk about is scalar multiplication. Scalar multiplication, the way I like to describe it, is distributive property. Because that's what it acts like. It's not distributive property, but it sure acts like distributive property. And it's like you guys act like an adult, but you're really not. You know, sometimes, you know, I act like I'm a responsible 35-year-old man. I'm not. I'm 35, but I don't know if I'm responsible or not. So depends on what I forgot to do at the house this morning before I left, I'm sure. So I'm sure there was something. So scalar multiplication acts like distributive property, but it's not. But gosh, it acts like it. It means multiply everybody in the matrix by the number that's on the outside. That's what scalar multiplication does. So everybody on the inside gets multiplied by -2. So you see why it acts like distributive property. That's why I say that, you know, it's not distributive property, because we're not distributing across addition or subtraction. We're distributing across a matrix, which is scalar multiplication. So it's a -6, -12, -8. Exactly, and that's what I want you to realize, that scalar multiplication is easy to do without the calculator. It's so much quicker, you know, just to do that. Now, if that was a fraction out in the front, and some of you might struggle with that, maybe it can be done with the calculator. All you got to do is enter the matrix, and then when you type, you know, you can type in -2 times, and then go get that matrix, and it'll do the scalar multiplication, give you that back out of that. It can be done in the calculator. I don't usually do it in the calculator. You just say -2 times whatever matrix, whatever your scalar multiplier is out in the front, say that times whatever matrix that you want to multiply it by, and that'll do it with the calculator. All right, so that's scalar multiplication. Let's do addition and subtraction. Yeah, addition and subtraction. One of the major things. Anybody remember doing this in Algebra 2? What do they have to be to add them? Be able to add them? They got to be the exact same size. So same size. Okay. Got to be the same size. If they're not, you can't add and subtract them. It's undefined if they're not the same size. So let's do this one. We got a 2, -6, -5, 8, 10, -11. What size is that one? 3 by 2. So if I'm going to add a matrix to it, I got to have another one that's what size? 3 by 2. So I'm going to use -5, -8, 13, 6, -14, 4. This can be done in the calculator. You just put, you know, this in as matrix A, this in as matrix B, and tell it A plus B. I don't do it in the calculator because it's quicker to just go, okay, 2 plus -5, -3, -6 plus -8, -14, -5 plus 13, 8, 8 plus 6, positive 14, 10 plus -14, -4, -11 plus 4, -7. And we've got the, you just add the corresponding parts. That they're, each individual piece in a matrix is called an element. So if I say element, I mean a piece inside the matrix. So the matching elements is what you add together, or subtract. If you do subtraction, you subtract the matching elements. First spot minus or plus the first spot. Just match up the spots and do the operation with that. Again, you can do it in the calculator and it'll spit it out and work for you. But I usually don't, just because it takes me longer to type them in than it does just do the math. Okay. All right. Multiplying matrices. Does anybody remember the rules for multiplying matrices? Because they do not have to be the same size. You would think they would, but they don't. Actually, there are times when they are the same size and you can't multiply them. Switch that around. It's columns in the first one. It's good because when you name the size of a matrix, it's number of rows by number of columns. So on the left matrix, row by column. The right matrix is rows by columns. And remember that these have to match. If they don't match, you can't multiply them. So like you have to, maybe you had a 3 by 2 and a 2 by 4. Since those two match, you can multiply them. Since the 2's in the middle match, the resulting matrix will be a 3 by 4 out of that. Okay. Rows and columns in the first one must match the rows in the second one. Matrix multiplication cannot be swapped with order. Like, 2 times 3 is the same thing as 3 times 2 with regular numbers. It's not the same with matrices. Matrices is not multiplication of matrices is not commutative. That went one. Almost done. What's confusing about it? You had this in Algebra 2. Come on. All right, so for multiplying matrices, the number of columns in the left one has to match the number of rows in the right one. Here we have an example. We have a 3 by 2, 3 rows by 2 columns, and a 2 by 1. The columns in the left one matches the rows in the right one. These are obviously not the same size, but it is legal to multiply them. I am not asking you to multiply them by hand. That takes several operations per row. But what I do want you to know is that if you multiply these two together, you're able to do that because these numbers in the middle match. And the answer is going to be a 3 by 1 from the outsides. It's always going to work that way. Okay? And then we're going to use the calculator to get it to multiply these for us. If you want to know how to do it by hand, I can quickly go through it. You say 2 times 10 plus negative 3 times 11. That gets you the first spot. And then you take 5 times 10 plus negative 7 times 11, and that gets you the second spot. And then negative 8 times 10 and 12 times 11, and that gets you the third spot, the 3 by 1. When they get bigger, it gets much longer, and each spot has several operations that you got to do. So, but I don't expect you to do this by hand. I expect you to do it with a calculator. So matrix, I need to edit. Matrix A is going to be a 3 by 2, 2, negative 3, 5, negative 7, negative 8, 12, and then I need matrix B to be a 2 by 1 in this case, and it's 10, 11. Go back to the regular calculator screen and then just grab each matrix, matrix A times matrix B. And it gets that 3 by 1 that we expected, negative 13, negative 27, positive 52. Now, if that operation is not defined and you try to multiply them together, it's going to give you an error. And it'll be, I think that this calculator gives the dimension mismatch error is what it tells you is wrong. There is the dimensions don't work for that. All right. So multiplying matrices, remember this one has to match that, and then the outsides are the size of the solution. That's just some theory that you probably need to know, and then do that in the calculator is what I'm asking you to do. No, it doesn't get this section. These two sections don't get harder. All right. Inverse matrices. Only happens with square matrices with determinants that are not equal to 0. If the determinant of a matrix is 0, you can't invert it. It's the inverse of a matrix is kind of like the multiplicative inverse of a number, or the reciprocal of a number. Like the reciprocal of 3/5 is 5/3. That's the inverse of that. With a matrix, an inverse matrix is kind of like the reciprocal. Is the way we treat that. What I want to be able to do is find a matrix that is the inverse of matrix A. And let's say we have this matrix 3, 1, 2, 1. And we want to find A inverse. To do this by hand, it takes row operations, several of them, to create an inverse matrix. To do this the way that I'm asking you to do this it takes putting it in the calculator and finding the inverse. So I'm going to put that matrix in the calculator. It's a 2 by 2. 3, 1, 2, 2, 1. And your calculator has an inverse button. It's this button right here. So I'm going to get the matrix, second matrix, matrix A, and then I'm going to hit the inverse button, which is the button directly below the one that says math. And it puts this little -1 exponent there. That means inverse. Hit enter. And there's the inverse. If you want to verify, this is the last thing, an inverse. Verifying inverses, here's what happens. If you multiply the original matrix times its inverse, then you'll get the identity matrix that's the same size. So for these two problems, if I say, 3, 1, 2, 1 times that inverse, 1, -1, -2, 3. When I multiply those two together, I get the identity matrix, and the identity matrix is just remember the ones and zeros that we get with our REF on the left side of the augmented matrix? That's an identity matrix. Since these are 2 by 2s, you get a 2 by 2 identity matrix. 1 and then 0 and 0, 1. If they were 3 by 3s, you'd get 1, 0, 0, 0, 1, 0, 0, 0, 1. And ones are in the diagonal. That's exactly the pattern you're looking for. If they are inverses. If you get anything else when you multiply them together, they're not inverses of one another. So to verify if two matrices are inverses, you multiply them together. And if you don't get ones in the diagonal and zeros everywhere else, they're not inverses. No, have to start at top left and go to the bottom right. Left to right diagonal. Good question, because I said diagonal. So. It'll like the questions will be like, are these two matrices inverses of one another? So just multiply them together, and that's the determination of it that they're inverses. All right. So the problems I would like for you to look at on page 878, 7 through 42, page 893, 9 through 40, then skip a bunch to 67 through 70. Out of that. Tomorrow, let's look at work day until right at 9, and then we'll quiz over this around 9 o'clock. That way we don't come back Monday and have to do a quiz after being out for 3 days. I think that's the best thing we can do. And that'll save us a little bit of time as well.